In this video, we will be dealing with series and compound DC generators. How do we construct a series DC generator? So here we have a model of the series DC generator. So it has an armature circuit in series, and in series to that circuit is the field circuit. The field circuit is made of a few turns of heavy wire, since it carries also the load current. So unlike the shunt field that we seen a while ago, a series field carries also the load current, since this is also in series with the load if a load is connected. So the series field has to be constructed using large wires or heavy wires with a few number of turns so that the resistance doesn't get very large. So these are the working equations for the series DC generator. So again, we see that the armature current, the series field current, and the load current are all equal because they're all in series. This is the terminal characteristics of the series DC generator. When we start a series DC generator, it has to be connected to a load. Uh, since without the load, there will be no current, and if there's no current, there will be no series current and no field flux. So therefore, there will be no E sub A generated, well, except for the residual voltage that it initially has, no, as shown here. So initially, the terminal voltage will increase with a load current, and in fact, almost the same as the increase in E sub A. However, as the load current uh, increases, there is a point here where the terminal voltage starts to decrease. The reason for that is that the load current is too large, that the voltage drops um, is having a serious effect on the terminal voltage, and instead of the terminal voltage increasing, it starts to decrease from this point as the load current continues to increase. Let's go to a compound DC generator. So we have two types for this in terms of how the flux interacts between the two fields. So we have a cumulatively compounded DC generators. Uh, so the model looks like this for a long shunt cumulatively compounded DC generator. So this is the armature circuit, this is the series field circuit, and this is the shunt field circuit. So a compound generator has two fields. We have the series field and the shunt field. So the series field is exactly the same as the field for the series DC generator, and the shunt field is exactly the same as the shunt field described in the self-excited DC generator. Um, This generator is called cumulatively compounded because the fluxes produced by the series field and the shunt field are additive, so they work together to produce a higher field flux or magnetomotive forces. And the tendency is for it to produce a larger E sub A compared to a differentially compounded DC generator that we will discuss after this. So these are the working equations for this generator. So this is for the long shunt uh, compound generator. We call it a long shunt because the shunt field is connected across the series combination of the armature circuit and the series field circuit. So let me rewire the field circuit so that it will be adjacent to the um, armature circuit. So here we'll see that in a cumulatively compounded generator, the net effect of the two fields are additive. So for example, the series field here produces a flux and both fields are oriented such that when they strike the windings of the armature, their fields are additive. This is the circuit for the short shunt type of the compound generator. So the shunt field is connected in parallel only to the armature circuit, and the series field is now in series with the load. This is the terminal characteristics of a cumulatively compounded DC generator. So we have three three plots. For example, if you have so the plot depends on the design of the series field. So for a series field that only contains a few number of turns, we have what is called the undercompounded uh, terminal characteristics. So the terminal characteristics there is about similar to the terminal characteristics of a self-excited DC shunt generator. So as the load current increases, the terminal voltage decreases. If we increase the number of series turns, we will get what is called a flat compounded, where the full load voltage is almost the same as the no load voltage. So you will get a voltage regulation there that is zero. So in terms of voltage regulation, this is a very good configuration for the compound generator. And if we even add more series turns in the series field, we'll get what is called the overcompounded. And this one will have a higher full load voltage than the no load voltage. And it is in this case that you will get a negative voltage regulation. So how do we explain the terminal characteristics of a cumulatively compounded DC generator? So initially, uh, as I sub A increases, the voltage drop across these series combination will increase. So this will tend to decrease the terminal voltage Um, this is usually true for flat or undercompounded DC generators. As Isabel increases, because the load Isabel increases, the field flux becomes stronger. The field flux produced by the series field becomes stronger. Um, thus, this will increase the total flux generated by the generator. This increase in flux will increase E sub A, which so this will increase in I sub A, or increase in I sub L, and this increase will tend to increase V sub T. So in here this tends to decrease V sub T because of the drop in RA and RS. This tends to increase V sub T. So the two will fight over what happens to the terminal voltage, and which predominates, uh, or what happens to the terminal voltage depends on which of these two factors predominates. If the increase in Vt due to the increase in flux has a greater influence over the voltage drops, then you will have an overcompounded um, compound DC generator. But if the drop is predominating the increase in the voltage due to the increase in flux, then you will have an undercompounded generator. So somewhere in between, you will get a flatly compounded DC generator. How do we control the terminal voltage of a cumulatively compounded DC generator? Well, it's the same as the um, some of those types that we have discussed earlier. So we can do this by changing the speed of rotation, which we normally don't do in actual practice. So uh, we usually do it by changing the field current. Now let's go to differentially compounded DC generators. So the circuit is like this one. So it looks so for this is for the long shunt, and it looks similar to the cumulatively um, compounded DC generator, except that our series field is now reversed. So earlier we have the dot located in here. So the fact that it is now on the right side means that in this drawing we actually reverse this connection uh, that we had on the previous diagram. We maintain the connection for the shunt field. So because we have reversed the series field, uh, the fluxes produced by the two fields will now be subtractive. They will oppose each other to produce a smaller net flux. Uh, well, we could have maintained the connection for the series field and instead reverse the shunt field. That we could still produce two opposing fields. So again, reorienting the fields to show how the fluxes affects the armature circuit. So for the series field, we have that flux there, and for the shunt field, we have that flux produced by that field. So clearly, they are opposing each other, so they are subtractive, and this will have an effect, a decreasing effect on E sub A. So these are the working equations for this configuration. So this is the terminal characteristics of a differentially compounded DC generator. So as the load current increases, the terminal voltage decreases and even comes to a point where the I sub L is actually decreasing while the terminal voltage is decreasing as well. So let's explain the terminal characteristics of the differentially compounded DC gen. So as I sub A increases, the drop across this series combination will increase, and that tends to decrease V sub t. Likewise, as I sub increases, this will increase the series field, because take note that the series field is current is almost the same as the load current. I sub f is almost uh, unchanged. So an increasing series field, since it disopposes the field produced by the shunt, will produce a lower net flux on the poles, and this will greatly decrease A sub A and therefore V sub T as well. So both the voltage drop and the increasing shunt series field flux will have a decreasing effect on the terminal voltage, and the combination of the two will have a drastic decrease on the overall terminal voltage, and thus the terminal characteristics that we have seen on the previous slide. So let's have one example for a compound generator. So here we have a 50 kilowatt to 250 short shunt cumulative compound generator. So this is the rating of that generator. And these are the resistances of the armatures, UVs, and the shunt fields. We also have a brush contact drop of 2 volts. So the question is, if the generator is delivering rated load, so meaning the load has these amount of wattage equals to the rated wattage or power of the generator. So we calculate the induced armature voltage, or E sub A. What is the required torque on the prime mover if 90% of the shaft power is converted to actual electrical energy, and the mechanical losses in B at rated load? Okay, so here is the solution. So first we compute for the load current. So that will be the load power, which is equals to the rating of the generator divided by the terminal voltage, which is also the rating. So we will get a current of 200 volts. We compute for V sub A, so we can actually use voltage divider to do that, or simply add V sub T with this voltage drop here. Again, take note that at steady state, these inductors here are shorted. So we have V sub A, 258 volts, and from there we can compute I sub F, and I sub A is I sub F plus I sub L. So this is our I sub A here. And then since we have I sub A, We can also compute for EA. Okay, so that answers our first question. And now that we have EA and IA, we can compute for the electromagnetic power that comes out of the armature circuit. Uh, Electromagnetic power comes from power in, and because of losses, only 90%. So according to the problem, only 90% of power in is converted to electromagnetic power. So from this relation, we can compute for P sub in, and that will give us 61 kilowatts. Now that we have P sub in, we can compute for the applied torque because we are given by its mechanical speed. So we will obtain an applied torque on the shaft equals to this result. We can compute for the mechanical losses by taking the difference of um, P in and the electromagnetic power, and that will give us this result. Take note that this result includes the core losses because it is between the P in and electromagnetic power. That's it for this video, and on our succeeding videos, we will discuss parallel operation of DC generators. This is being done if the load becomes too high that a single generator cannot accommodate such load. So instead of replacing the generator with a larger rating, we normally put another generator that is connected in parallel to the existing generator.